Vibration analysis, diagnosing looseness in rotating machinery, techniques for detecting mechanical instability and wear. Diagnosing looseness. This opening slide introduces the overarching topic of diagnosing looseness within rotating machinery systems. Looseness is a common mechanical fault condition involving unintended mechanical freedom between machine components, resulting in nonlinear vibration behavior. This slide sets the tone for the full presentation by emphasizing the relevance of looseness as a critical factor in reliability engineering, predictive maintenance, and asset health monitoring programs. The content prepares the audience for a detailed exploration of various types of mechanical looseness, including rotating looseness, structural looseness, and pillow block looseness. It highlights why looseness is often misdiagnosed and how proper diagnostics can prevent severe mechanical degradation, efficiency losses, or catastrophic equipment failure. This slide establishes the professional engineering context and invites participants to engage with the technical material that follows. Introduction. This slide provides an overview of what will be covered in the presentation, introducing the concept of mechanical looseness as a fault category within vibration analysis and machinery diagnostics. It outlines why looseness occurs, how it manifests in various machine configurations, and why understanding its signatures is essential for Category 2 vibration analysts. The introduction clarifies that looseness can exist at multiple levels within a machine, from internal bearing fits to external structural frameworks, and that each type produces its own vibration signature. By framing looseness as both common and highly misunderstood, this slide encourages participants to adopt a systematic and analytical mindset throughout the presentation. The content also briefly explains the relationship between looseness and related mechanical faults, providing context for the deeper analysis in subsequent slides. Rotating looseness. This slide explains rotating looseness, which occurs when there is excessive internal clearance between rotating components, most often between a rotor and its bearing. Participants learn that rotating looseness typically creates heavy impacting and multiple harmonics in the vibration spectrum, clearly distinguishing it from simple unbalance. The slide provides the theoretical background needed to understand the nonlinear dynamic interactions, such as impacts between rotor and bearing races, that produce the characteristic stairstep or distorted orbit patterns. This content covers common causes, including worn bearings, incorrect fits, and shaft flexing under load. These insights prepare the analyst to recognize early-stage looseness and differentiate it from more severe looseness conditions that may develop as the machine deteriorates. Why harmonics occur. This slide explores the physical basis for harmonic generation in cases of rotating looseness. Harmonics arise because looseness introduces nonlinear stiffness into the system, causing the machine to respond differently depending on rotor position, load direction, and impact severity. As the rotor contacts and then separates from the bearing surface cyclically, it generates sharp transient forces that manifest as multiples of running speed in the FFT spectrum. The slide also explains how the severity of looseness often correlates with the number and amplitude of harmonics present. Analysts learn that a harmonic ladder extending beyond 3 times or 5 times running speed is a strong indicator of significant looseness. Understanding these harmonic structures is essential for distinguishing looseness from misalignment or mechanical rubs, which may also produce elevated harmonics but with different accompanying symptoms. Example of looseness. This slide provides a practical example of rotating looseness, describing a real-world scenario such as a pump or motor operating with a worn bearing fit. It walks through the observable vibration characteristics, including repeating impacts in the time waveform, rising harmonic content in the FFT, and orbit shapes that flatten or become multi-lobed. The example demonstrates how looseness progresses, showing how early indications may be subtle but intensify rapidly as mechanical play increases. It also emphasizes the importance of monitoring trends, as looseness typically worsens with load changes, thermal expansion, and progressive material wear. This slide helps analysts visualize the fault, reinforcing theoretical concepts with field-applicable observation patterns. Key points: rotating looseness. This slide summarizes the essential diagnostic signatures of rotating looseness. It reinforces the presence of multiple harmonics, nonlinear behavior in the time waveform, and unusual orbits as the primary indicators. Analysts are reminded that these patterns differ substantially from common faults such as unbalance or misalignment. The slide outlines how rotating looseness typically presents with heavy one-times vibration accompanied by strong harmonic development. Additionally, the content stresses the importance of using both time waveform and orbit analysis, as looseness is often more apparent in these domains than in the FFT alone. This slide acts as a consolidation point to ensure learners retain foundational diagnostic principles before progressing to structural looseness. Structural looseness. This slide introduces structural looseness, a condition arising when the machine's support structure, such as the baseplate, grout, or foundation, lacks rigidity. Structural looseness alters how forces are transmitted from the machine to the foundation, often causing exaggerated movement at low frequencies and inconsistent phase behavior. The content explains how cracked grout, loose anchor bolts, corroded base structures, or improperly shimmed feet lead to this condition. Analysts learn that structural looseness usually produces less regular harmonic patterns than rotating looseness and may exhibit broad-spectrum vibration increases due to resonance interactions. Understanding these distinctions is crucial for proper fault categorization. Looseness versus unbalance. This slide compares looseness with unbalance, helping analysts avoid common misdiagnosis. While both faults may show elevated one-times vibration, unbalance typically produces a clean spectrum dominated by a single frequency with stable phase. Looseness, by contrast, often shows strong harmonics, inconsistent phase, and impact signatures. The slide explains why unbalance produces linear behavior while looseness is inherently nonlinear. This comparison helps participants understand why looseness often mimics unbalance in early stages but diverges significantly as the condition worsens, reinforcing the need for multi-domain vibration analysis. Phase measurement importance. This slide emphasizes the diagnostic importance of phase analysis in identifying structural looseness. Structural looseness often causes phase differences between sensors mounted on different parts of the structure, such as the machine feet or bearing housings. Unlike unbalance, where phase remains relatively stable across operating conditions, looseness may produce erratic or shifting phase readings as the structure flexes or moves. The slide explains how to interpret these measurements and how phase data can confirm whether the problem lies in the rotating element or in the supporting framework. Proper phase interpretation is crucial for confident diagnosis. Case study, structural looseness. This slide presents a case study involving structural looseness, commonly a pump or motor installed on deteriorated grout or an inadequately reinforced foundation. The case describes how the machine exhibited low-frequency vibration, inconsistent phase behavior, and broadband spectral content. Through inspection, analysts discovered loose or corroded anchor bolts or settling of the base. The slide reinforces how vibration data correlates with physical inspection findings, demonstrating the importance of a holistic diagnostic approach that integrates data interpretation with field verification. Key points 2 of structural looseness. This slide provides a comprehensive summary of the presentation, revisiting the core principles of diagnosing looseness in rotating machinery. It highlights the distinct signatures of rotating looseness, structural looseness, and pillow block looseness across vibration domains. The summary reinforces the role of harmonic analysis, time waveform interpretation, orbit analysis, and phase measurement in forming accurate diagnoses. The slide concludes by emphasizing the importance of integrating vibration data with field inspection findings to achieve reliable and actionable maintenance decisions. Loose pillow block bearings. This slide introduces looseness involving pillow block bearings, which occurs when the bearing housing becomes loose on its mounting surface due to bolt looseness, wear, or deformation. This fault condition creates unpredictable and chaotic vibration patterns because the entire bearing housing shifts relative to the support surface. Participants learn that pillow block looseness often produces heavy broadband vibration and intermittent impacts, making it one of the more dynamic and irregular looseness conditions. Understanding this behavior prepares analysts to interpret the unique vibration signatures associated with pedestal or pillow block looseness. Pillow block symptoms. This slide discusses the common symptoms associated with pillow block looseness. These include erratic changes in vibration amplitude, broadband noise in the spectrum, sporadic impact events in the time waveform, and sometimes frequency components that shift unpredictably with load or speed. The content highlights why this type of looseness is often mistaken for bearing defects or intermittent rubbing, emphasizing the need for careful waveform analysis and physical inspection. Analysts learn the importance of checking mounting bolts, alignment, and foot integrity in these scenarios. FFT pattern for pillow block looseness. This slide describes the typical FFT pattern for pillow block looseness. Unlike rotating looseness, which shows strong harmonics, or structural looseness, which shows low-frequency amplification, pillow block looseness often produces broadband spectral activity with irregular harmonic presence. The spectrum may appear noisy, with inconsistent peaks and random energy bursts due to the unpredictable movement of the bearing housing. This slide helps analysts identify the signature by comparing it with those of other looseness types, reinforcing accurate fault classification. Time waveform for pillow block looseness. This slide explains how the time waveform can be used to diagnose pillow block looseness. The waveform often contains sudden high-amplitude spikes and chaotic signal segments caused by the shifting of the bearing pedestal. These impacts may occur irregularly, differentiating pillow block looseness from rotating looseness, which tends to have more uniform impacts. The content stresses that time waveform analysis is one of the most reliable methods for diagnosing this fault type, making it essential for the analyst's diagnostic toolkit. Inspection checklist. This slide provides a practical inspection checklist to accompany vibration diagnostics. Key inspection points include checking for loose foot bolts, assessing the integrity of the baseplate or foundation, verifying shim condition, and examining bearing fits. The checklist emphasizes that looseness is often confirmed by physical inspection even when vibration signatures strongly indicate the fault. This reinforces the dual importance of field verification and data analysis in professional condition monitoring. Corrective actions. This slide outlines the corrective actions recommended for the various types of looseness discussed. Actions may include tightening or replacing bolts, remachining fits, injecting or repairing grout, realigning machinery, and reinforcing structural supports. The content explains that corrective measures should address root causes rather than symptoms, for example, replacing worn bearing fits rather than merely tightening bolts. The slide promotes best practices for sustainable machinery reliability. Summary of looseness diagnostics. This slide provides a comprehensive summary of the presentation, revisiting the core principles of diagnosing looseness in rotating machinery. It highlights the distinct signatures of rotating looseness, structural looseness, and pillow block looseness across vibration domains. The summary reinforces the role of harmonic analysis, time waveform interpretation, orbit analysis, and phase measurement in forming accurate diagnoses. The slide concludes by emphasizing the importance of integrating vibration data with field inspection findings to achieve reliable and actionable maintenance decisions.